Hello grade 12s, and welcome to the last video in the chapter Work, Energy and Power from the Answer series. In this video, we are going to summarize the contents of this particular topic. First, let's talk about work. We understand that work is done on an object when a force or a component of that force is parallel to the displacement of the object. By making work the product of force and displacement, we are getting a unit of joules, which should convince us that work done and energy transferred are the same thing. Neither of them have direction, so work is a scalar quantity. We use the definition formula to calculate work done by each force. Use a free body diagram to make sure you don't leave out any forces. We have three typical displacements: horizontally, vertically, or up and down a slope. If there is an applied force and friction when an object moves horizontally, then both these forces do work. The normal and the gravitational forces do no work because cos of 90 degrees is 0. When an object moves vertically, the weight and the tension and friction, if present, all do work on the object. The angle for tension and weight depends on the direction of motion, but the work done by friction will always be negative because cos 180 degrees equals -1. When an object moves up or down an inclined plane, both friction and the applied force, if present, do work on the object. The normal force does no work, as it is at 90 degrees to the displacement. There are three ways to find work done by the gravitational force. Either use the component of the gravitational force parallel to the slope, or use the whole force and delta y. This second method only works if you know the vertical height of the slope. The third method uses 90 plus alpha or 90 minus alpha as the angle between the two vectors. To generalize, friction is always in the opposite direction to displacement, so the work done by friction is always negative. Forces like the applied force can be at any angle to the displacement, from 0 to 180 degrees or anywhere in between. Gravitational force is always straight down, so it all depends on the direction of the displacement, whether or not gravitational force does any work. The only time the work done by the gravitational force equals 0 is when the displacement is horizontal. Each force does work. The works can be added together to get the net work. If you have the net force as a vector sum, then you can calculate the net work directly. Now, on to energy. We learned about these two forms of mechanical energy in earlier grades. Mechanical energy applies to objects moving and or positioned somewhere within the gravitational field of the Earth. That's how we deal with mechanical energy at school level. A force acting on that object does work. Equally, the object can apply a force to do work. Like work, energy is a scalar quantity with a unit of joules. There are two important energy principles that you're allowed to use in work energy calculations. The work energy theorem is generalized for any forces, both conservative and non-conservative forces. However, certain forces do not change the total mechanical energy. They are conservative, and then we can use the conservation law. If a question refers to using energy principles, then you are limited to one of these methods. Here is the statement of the work energy theorem. Let's read it together. The work done on an object by a resultant or net force is equal to the change in the kinetic energy of the object. The key word here is net. Either refer to the net force or the net work, but not both. Always start with this expression, and then you can expand it using delta EK, or maybe the sum of works, and or maybe the work definition. From grade 10, here is the law of conservation of mechanical energy. Let's read it together. In an isolated system, the total mechanical energy is constant. Keywords are isolated, total, and constant. Don't say conserved, then you're defining conservation using conserved, which doesn't take anyone's understanding forward. The expression contains a sigma sign from mathematics, and it uses I for the initial conditions and F for the final conditions. Examples of conservation of mechanical energy include a frictionless pendulum, an object in free fall, and an object sliding down a frictionless inclined plane. Notice how friction has been excluded from all three of these examples. Conservative forces don't change the mechanical energy of an object. They just convert potential to kinetic energy, or vice versa. It doesn't matter what the path is. Only the initial and the final positions count. Non-conservative forces act all along the path length, so it does matter whether the force moves the object over something, around something, through, or a straight line from initial to final position. We can derive from the general form of the work energy theorem an equation for work done collectively by all the non-conservative forces. Where you have a mixture of conservative and non-conservative forces at the same time, this is especially useful for separating them out. Finally, we get to power, which tells us how quickly work is done or energy is transferred. In physics, this is defined as a rate, and we calculate it by dividing by the time taken. We also derived a formula for power in terms of force and velocity. People, animals, engines all have power ratings that say how much energy in joules is transferred per second. The force causing the change in energy is typically non-conservative. For example, in a water pump. We can use the equation for work done by a non-conservative force and then determine the power required.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.